So we're going to look at the velocity problem next. This was the other scenario that we discussed in lesson one, where we were trying to find an instantaneous velocity as a using average velocities that were found over smaller and smaller intervals of time. So before we do that, I just want to kind of back up a little bit and talk about the basics of the type of motion we're discussing in this class. And so it's important that you realize it's assumed to be of an object moving along a coordinate axis, which means back and forth, left to right, or up and down. That is the only motion that we're analyzing in this situation. So that could be an object like dropped straight down, or perhaps thrown, but again, it has to be straight up. We're not dealing with breaking, motion in a parabola into different forces or anything like that. It's just straight up and down. Or you could have maybe an object moving back and forth on a track. A straight, like horizontal track. So those are the kinds of motion that we're talking about. And we usually use S, the letter S, right here. Oops. Let's see if we can get this to work. S of t, we use S to stand for the position function. So in other words, S will be the location along the up and down or the left and right at the time t. Okay. And now it's kind of confusing because we can't actually graph S position versus time curves in 2 dimensions. That doesn't mean it's what the movement is. It's just tracking the position up or down or left or right over time. Okay, so we're going to just mess with a couple of these position versus time curves so that you can get used to seeing them and see how they are a little different than the actual motion we're talking about. So let's say we start with a car that's moving only in the positive direction. Okay, so as t increases, s increases. The position gets bigger. Okay, and so we're going to sketch a position versus time. So s would be this way. Sorry, that is not s. T. T would be here. So, as time, maybe it's minutes, maybe it's seconds. And then the position would be here. And I'm not necessarily going to give it a specific, my T is kind of in the middle there. That's better. So wherever this car starts at t equals 0, what we do know is it moves only in the positive direction. So when the t increases to 1, the s has to have gotten bigger. I don't know how much bigger. And then when I get to t equals 2, the s has to have gotten bigger still. Every time my t increases, my position increases. So I could have a straight line, or maybe it's not a straight line, but that's what it would look like for something that is moving only in the positive direction. It never goes backwards. So, it's always going this way. So if you're counting position, the position is always getting higher. Okay. So let's contrast that with the next picture. Now I have a position versus time curve right here. And you can see as time goes on till about 1.5, who knows, seconds. I guess that's what the S probably stands for. The position is increasing. But then from 1.5 seconds to 3 seconds, what's happening to the position? All of these Y values are getting smaller. So could you come up with a possible scenario that this is modeling, that this could be the position versus time curve? There are a lot of different options. I've heard a lot of people say maybe a ball. thrown up, like straight up in the air, because then it's going to fall down. Gravity. So it went up until this would be the part of it being thrown up, and this would be the part of it falling back down. I've heard that same car drives forward, then reverses. And again, along the same line. Like, oops, I forgot something. I got to go back. Yep. So just want you, I think the worksheet for this particular lesson also has a few more of those where you can try to interpret what's happening. What is this position versus time curve trying to describe in terms of motion? Okay. So we're going to move past that a little bit and go back to talking about average velocity, which we did in lesson 1. If we were talking about average velocity over this time interval. So remember, average velocity is the change in position over the change in time. So if I am talking about this time interval from t to t plus h, similar to what we had just done, the change in time would be h. And we were going to just use our position curve, our position function, to say that the position at t plus h minus the position at t all over h, that's your average velocity. And if you remember, we talked about this corresponding to the slopes of the secant lines on those position versus time curves. And so we kind of realized, oh, average velocity and secant line slopes are the same. So guess what? Instantaneous velocity and tangent line slopes are going to be the same. So that average velocity is describing behavior over an interval. But if we want the instantaneous velocity at one instant, then what are we going to do? We're going to look at this time interval and we're going to try to take the limit of that as h goes to 0. Pretty similar to what we just did. So if we take the limit as h approaches 0, oh, that should say of, not if, of the average velocity over that same interval, then we will arrive at the instantaneous velocity at that one time. So that is our definition. The instantaneous velocity, which we will just call v of t, at time t equals a, is velocity at the moment a is the limit as h approaches 0 of s of a plus h minus s of a all over h. So once again, pretty much the same limit calculation, and the function that we are using is the position function. And as we just discussed, this corresponds to the slope of the tangent line to the position versus time curve at t equals a. Okay, so we do have one example here to work through. We've got a stone. It's dropped from a height of 144 feet, falls straight down. With the height of the stone, the position function given by this negative 16t squared plus 144. So when will the stone hit the ground? And find its velocity at that time. So we have a couple of different things. The first thing we need to know is when will the stone hit the ground, and then we will find the velocity at that time. So all we have is a position function. Remember, position at this point will be height. So how do we figure out using the position function when the stone hits the ground? What position will the stone be in when it's on the ground? It will be at 0. So this would be when S of t is 0. So I'm going to come over here on the side. I'm going to set that position function equal to 0. Looks like I'll have t squared is whatever 144 divided by 16 is, which is 9. So I will use only the positive square root since we're talking about time. And I know now that it's going to hit the ground in 3 seconds after it is dropped. So that answers my first question. But now I need to find the velocity at that time. So the velocity at 3 will be the limit as h approaches 0 of s of 3 plus h minus s of 3 all over h. So do you see that once again, I have started this process by just writing down the kind of the basic limit calculation I need to do. And then I'm going to start plugging in. So I need to plug 3 plus h into that entire function. Which is what I have here, negative 16, 3 plus h squared plus 144. That whole thing is what we get when we plug 3 plus h into this function. Then I need to subtract s of 3, but we already know what s of 3 is. S of 3 is 0, right? That's when it's hit the ground. So again, if you were to try to plug 0 in right here, you're going to get 0 over 0. And so we got to do some calculations. I'm going to have you go ahead and press pause and spend a little time trying to work through this limit. All right, so I did some calculations here, basically just FOILed this out first, distributed my negative 16, saw that my constants canceled on the top, factored the h out of the bottom, and then I'm finally able to go ahead and substitute in the h equals 0, and I get negative 96. I should have some units here. It looks like we are measuring in feet and seconds. So that would be feet per second. Okay.